This is the second of the two revision videos looking at the differentiation topic of the FP1 module. The first of the two videos looked at differentiation from first principles, and in this video we are going to consider the work on logarithmic differentiation. Now, the key fact that we're going to be using time and time again is that if we want to differentiate the logarithm of a function of x, then the chain rule will give us the derivative of that is the derivative of the function, so that's g dash x, divided by the function itself, g of x. There are a lot of prerequisites from other modules for this particular topic. We need clearly to be familiar with the idea of natural logarithms and their basic rules. We need to be familiar with the differentiation of trigonometric, exponential and logarithmic functions. And we need to be familiar with the product rule, the quotient rule and the chain rule for differentiation. So, for our first example, let us use the process of logarithmic differentiation to try and find the derivative of 2 plus x squared to the power 4 divided by the square root of 1 plus x to the power 4. The first step is to take the logarithm of each side. So in other words, we're going to try and express ln of g of x in terms of logarithms. Well, straight away we can say that ln of g of x is the ln of 2 plus x squared to the power 4 over the square root of 1 plus x to the 4. Now the square root of something is something to the power of half, so we could equally well write ln of g of x as the logarithm of 2 plus x squared to the power 4 divided by 1 plus x to the 4 to the power of half. Now at this stage we need to remember some of the rules of logarithms. In particular, at this stage, we've got the logarithm of something divided by something else. We've got the logarithm of 2 plus x squared to the power 4 divided by 1 plus x to the 4 to the half. And our rule of logarithms tells us that the logarithm of p over q is the same thing as the logarithm of p, take away the logarithm of q. So we can replace the logarithm of 2 plus x squared to the power 4 divided by 1 plus x to the 4 to the half by the logarithm of 2 plus x squared to the power 4, take away the logarithm of 1 plus x to the 4 to the power of half. And we can use another of the rules of logarithms to do a little bit more simplification. We know that the logarithm of p to the n is the same thing as n times the logarithm of p. So the logarithm of 2 plus x squared to the power 4 can be replaced by 4 times the logarithm of 2 plus x squared, and the logarithm of 1 plus x to the 4 to the power of half can be replaced by a half of the logarithm of 1 plus x to the 4. Now what we started off with was a horrendously complicated expression. Ln, the logarithm of g of x, was the logarithm of 2 plus x squared to the power 4 over 1 plus x to the 4 to the half. And using the rules of logarithms, we've been able to simplify that to 4 times the logarithm of 2 plus x squared, take away a half times the logarithm of 1 plus x to the 4. We can now differentiate both sides. And in order to differentiate both sides, we're just going to make lots and lots of use of the standard result, which said that if we've got the logarithm of a function, then the derivative of that is the derivative of the function divided by the function itself. So, logarithm of g of x, if we differentiate that, we just get g dash x over g of x. Now we've got 4 times the logarithm of 2 plus x squared as the first term on the right hand side. So the derivative of that is going to be 4 times the derivative of ln of 2 plus x squared. If we differentiate the logarithm of 2 plus x squared, we're going to get the derivative, that's 2x, divided by the original function, which is 2 plus x squared. So the first term on the right hand side is going to differentiate through to 4 times 2x over 2 plus x squared. Now we've got the second term on the right hand side to think about, which is a half logarithm of 1 plus x to the 4. So the derivative of that is going to be a half times the derivative of the logarithm of 1 plus x to the 4. The logarithm of 1 plus x to the 4 is going to differentiate to give us 4x cubed on the top. That's the derivative of the 1 plus x to the 4, divided by the original function bit, divided by the 1 plus x to the 4. So the result of differentiating is that we have g dash x divided by g of x is 4 times 2x over 2 plus x squared. Take away a half of 4x cubed over 1 plus x to the 4, which can be tidied up slightly to give us 8x over 2 plus x squared. Take away 2x cubed over 1 plus x to the 4. So we've got an expression for g dash x divided by g of x. Or we want an expression for g dash x. We want an expression for the derivative of g. So all we need to do at this stage is multiply up by g of x. So we've got g dash x, the derivative of g of x, is 8x over 2 plus x squared, take away 2x cubed over 1 plus x to the 4 times by g of x. Or in other words, we've got g dash x is that horrible bracket times by the original function. So there we are, we've managed to differentiate that really rather nasty looking function without needing to resort to chain rules or quotient rules. Okay, let's now have a look at an example on logarithmic differentiation from the January 2012 paper. And the function that we are considering this time is the function f of x equals sine x to the power x. And the first part of the question, we've got to use some logarithmic differentiation to show that f dash x can be written as f of x times g of x. And we've got to determine what g of x actually is. So, just as in the previous example, the first thing we're going to do is if we're going to try and perform a logarithmic differentiation, we've got to consider the logarithm of f of x. So the logarithm of f of x is the logarithm of sine x to the power x. And if we remember our rules of logarithms again, we know that the logarithm of p to the n is the same thing as n times log p. So the logarithm of sine x to the power x is going to be the same thing as x times the logarithm of sine x. Now, we can actually differentiate the left-hand side and the right-hand side. If we differentiate the right-hand side, we're differentiating the logarithm of a function, so we just obtain the derivative of the function divided by the original function. So we obtain f dash x divided by f of x. We then need to differentiate the right-hand side. Now the right-hand side consists of x times logarithm of sine x. So we're going to have to use the product rule in order to do the differentiation of that. So using the product rule, we first of all need to differentiate the x, which gives us 1, and leave the logarithm of sine x alone. And then we add the x left alone times by the derivative of the logarithm of sine x. And the derivative of the logarithm of sine x is going to be derivative of sine x divided by sine x. Derivative of sine x is cos x. So we're ending up with, having used the product rule, that f dash x over f of x is the same thing as 1 times the logarithm of sine x plus x times by cos x divided by sine x. It's important to notice that we needed to use the product rule to effect that differentiation of the right-hand side. Well, we're aiming to find f dash x. So at this stage now we can simply multiply through by f of x. So we've got f dash x is f of x times by the logarithm of sine x plus x cos x over sine x. In other words, we have shown that f dash x is equal to f of x times g of x, where g of x is the logarithm of sine x plus x times cos x over sine x. Now we just need to remember a little bit about our trigonometric functions. Cos x over sine x is precisely the same thing as cot x, so we can write g of x as being the logarithm of sine x plus x times cot x. So that means that we've managed to do the first part of the question. Let's move on to the second part now. We're told that the graph of f has only got one stationary point. So we're being asked to show that its x-coordinate must be somewhere between 0.39 and 0.40. Well, the stationary point is the point where the gradient is 0. So in essence we're trying to find out the point where f dash alpha or f dash x equals 0. So we're trying to show that there's a solution of f dash x equals 0 lying between 0.39 and 0.40. Okay, now the first thing to notice here is that we've got x lies between 0 and 1. Now 1 is definitely smaller than pi by 2, so we can be quite certain in our own mind that sine x is going to be a positive number, and therefore f of x, which is sine x to the x, is definitely a positive number, whatever the value of x is between 0 and 1. Now, if we think about g of 0.39, our calculator will tell us, remember we're using radians, our calculator will tell us that g of 0.39 is minus 0.018, and g of 0.4 is 0.00299. So f dash 0.39 is f of 0.39, which is we know is a positive number, times by g of 0.39, which we know is a negative number. So we've got a positive times a negative, which is definitely a negative number. So we know that f dash 0.39 is definitely a negative number. On the other hand, f dash 0.4 is f of 0.4 times g of 0.4. We know that f of 0.4 is definitely positive, and we've shown that g of 0.4 is positive, so f dash 0.4 must be positive. So we've got the f dash 0.39 is negative, f dash 0.4 is positive, so therefore there's going to be a value somewhere between 0.39 and 0.40, which has got f dash alpha equals 0, and that's going to be the stationary point of f. And we now need to move on to the final part of the question. We've got to show that the second derivative of f of alpha is f of alpha times g dash alpha. So where are we? We need to go back. We know that f dash x is f of x times g of x. So if we want to start thinking about the second derivative of f, we're going to need to differentiate f of x times g of x. So we've got f double dash x, the second derivative of f, equals the derivative of f of x times g of x. Now again, we've got a product here. We've got f of x times g of x. So we must use the product rule to do the differentiation. So if we use the product rule on f of x times g of x, we get the derivative of f times g plus f times the derivative of g. So we know the second derivative of f of x is f dash x g of x plus f of x g dash x. So putting x equal to alpha, we've got f double dash alpha is f dash alpha g of alpha plus f of alpha g dash alpha. But alpha is the x-coordinate of the stationary point, so we know that f dash alpha must equal 0. So that now tells me that f double dash alpha is 0 times g of alpha plus f of alpha times g dash alpha. In other words, we've got f double dash alpha is f of alpha times g dash alpha, which is what we were asked to show. I've got the final part of part C still to do. We know that f double dash alpha is f of alpha times g dash alpha, and we know that f of x is always positive for any value of x lying between 0 and 1, so we're quite certain that f of alpha is positive. Right, we're going to have to think about what this g dash alpha might be. Well, we know that g of x is the logarithm of sine x plus x times cot x. So we've got a bit more differentiation to do. So differentiating, we've got g dash x is, first of all, the derivative of the logarithm of sine x. And we've already dealt with that once earlier in the question. The derivative of the logarithm of sine x is the derivative of sine x cos x divided by sine x, so that's just cos x over sine x. But now we've also got to differentiate x cot x. And this again is going to require us to use the product rule, because we've got x times by cot x. So when we use the product rule, we're going to have 1 times cot x plus x times by the derivative of cot x. And the derivative of cot x can be found within the formula booklet, or can be shown to be minus cosec squared x. So, doing a little bit of tidying up, we've got g dash x is cos x over sin x, which is cot x, plus 1 times cot x, which is another cot x. Take away x cosec squared x. So we have g dash x is 2 cot x. Take away x cosec squared x. So we can now find, using the fact that we know that alpha is 0.399, we can find the value of g dash alpha from our calculator, which comes out to be 2.1. Now that in turn tells me that f double dash alpha is f of alpha times g dash alpha. F of alpha is positive, g dash alpha is positive, so f double dash alpha must be positive. So we know that alpha is a stationary point. We've seen that f double dash alpha is positive, so that enables us to deduce that the stationary point is a minimum. Finally, let's just review the marking scheme for this question. The first part of the question took 4 marks. The first mark was given for simply considering ln of f of x and obtaining the result x times the logarithm of sin x. The next 2 marks for carrying out the differentiation and using the product rule appropriately. And then finally, the final mark there was for obtaining g of x. For part B, the first mark was simply for observing that we needed to find a solution of f dash x equals 0 if we wish to find the stationary point. And then the next 2 marks were for showing that because f dash 0.39 was less than 0 and f dash 0.40 was bigger than 0, then there must be a solution of f dash x equals 0 between 0.39 and 0.40. Moving on to part C, the first result had 3 marks, 2 marks for obtaining an expression for f double dash x, and then the third mark for making use of the fact that we knew that f dash alpha had to equal 0 to obtain the given result. The final 4 marks in the question, 2 were assigned for finding g dash alpha, and then the final 2 marks were for making use of the fact that once we knew that g dash alpha was positive, that implied that f double dash alpha had to be positive, and hence that the stationary point had to be a minimum.